Hello, now let us solve the problem together. So here f is a function which we know is continuous everywhere on R, and we know that this number a, which appears here, is just a real constant. And then we define a function g of x, which depends on a positive parameter h in this way. So you can assume that h is a fixed when you want to define this. For every positive h, we define a new function that depends on that h, okay, in this way. It is 1 over that h if x lies somewhere between, in the closed interval from 0 to h, and it becomes 0 otherwise. And then we want to calculate this limit of this integral when h approaches 0 from the right-hand side. So first of all, I want you to understand what is happening here. This is an integral, and the variable of the integral is x. And a is also fixed. So what happens here? When you integrate over x, when a is left, you will not get a number. You will get something which depends on the value of h that you choose. Okay? So this means that if I want to interpret this expression is a quantity that depends on h. So this is a function of h. So this is completely sensible to ask what is the limit of a function of h when h approaches 0 from the right side. So don't look at it as an integral, so you can see that this is a function of h, and this is why this is completely sensible to ask that question. Okay, how we should solve that problem? We can assume that a positive h is given to me. First of all, when h approaches 0, when I am interested in calculating this limit when h approaches 0, it means that I can assume that h is a small. Okay, so let me just try to draw some diagram here for you so that you can understand this problem a little bit better. So let us try to draw the graph of g of x for a fixed positive h. So let us assume that h is given to you, you want to draw the graph of this function. Okay, so h is some positive number. So let me take h to be here. Okay, we know that the function g of x is 0 if x is less than 0 and greater than h. So this means that, and by the way, here is 0. So if I am on the left-hand side of the origin, the function is defined to be 0. So if I want to draw the graph of that, it becomes just a horizontal line on the x-axis. But I exclude the origin from here because x equals to 0 is not included. And it is also 0 after h. So this means that I put a hollow circle here, meaning not including h. Then on the right-hand side, the function is again 0. But when it is in the closed interval from 0 to h, the function is a constant. But which constant? 1 over h. What is h? h is the number that I have chosen. Okay? So whatever h is, 1 over h is a constant. So let us assume that this is my 1 over h, somewhere here. And then between these two intervals, so it is like this. So here, it's also a constant function, but at the height of 1 over h. So let us just put these dotted lines for guidance. So this orange, whatever you see in orange, is the graph of this function for a specific choice of positive h. Okay, and now we want to calculate this integral, starting from -1 up to 1. So -1 is somewhere here, for example. Okay, so I start from -1, I go up to 1. Here it is not clear where 1 is, because I don't know what h is. Might be h is larger than 1, so 1 should be somewhere here. Or might be h is smaller than 1, then 1 would be outside that closed interval. But because h is supposed to go to the 0, approaches 0, so this means that if I want to calculate this, I do not care about the values of the function when h is large. I want to look at the function when h is a small. So if that h is a small, so I can safely assume that h lies within the interval from 0 to 1. So let me just do that. So let us assume that 1 is somewhere here, and then I will take that 1. So this would be minus 1, yes? For example, yeah, it's not important to be very precise here, but this is my picture here. And now forget about the limit part. Let us concentrate on calculating this integral if possible. So I want to calculate this integral from minus 1 up to 1, but I know that the function g changes its form on the way. When it goes from minus 1 to 0, the function is 0. When it goes from 0 to h, the function is constant 1 over h. And when it goes from h to 1, again the function becomes 0. So integral from minus 1 to 1, f of a minus x, gh of x dx can be broken into three integrals. From minus 1 to 0, f of a minus x, but here g of x is 0 on that interval, dx, plus from 0 to h, you see, but the function f of a minus h, but this time gh of x is actually 1 over h dx, and then plus integral from h to 1, and then I have f of a minus h, again the function g is 0, d of x. Okay, so if this is 0, this product becomes 0, so this integral vanishes. The same here, this integral vanishes. And 1 over h is a constant, so I can pull it out. So this becomes 1 over h integral from 0 to h f of a minus, oh, it was not minus h. This is f of a minus x, sorry. Okay, so this becomes f of minus x dx. Okay, and now I want to take the limit when h goes to 0 from the right-hand side. One thing you can do, you can use the Hopital's rule. Okay, I will solve this problem now in two different methods. So method 1, I want to use the Hopital's rule. Why the Hopital's rule is applicable? Okay, so I can imagine this in this form. I can write it as integral from 0 to h f of a minus x dx over h. And I want to take the limit of integral from 0 to h f of a minus x dx over h when h goes to 0 from the right-hand side. Is the Hopital's rule applicable here? The answer is yes, because when I send h to 0, the denominator becomes infinitesimal, and when h approaches 0, integral from 0 to 0 is also 0, so this limit is indeterminate of the form 0 over 0. So the Hopital's rule is applicable. So I differentiate the numerator and the denominator separately. The derivative of the denominator with respect to the variable h itself is just 1. But then I use the fundamental theorem of calculus to differentiate this. So you know that if you want to differentiate that, what you can do, you can write f, and so you can assume that this function, I can call it s of x. But the important thing that s of x is continuous. Why? Because f is continuous everywhere on R. A minus x is a first degree polynomial that is also continuous. So the composition of two continuous functions is actually a continuous function. So s of x is continuous function, so I can apply the fundamental theorem of calculus to differentiate that. So, and hopefully you know what is the rule. You need just to replace x with h. So this is just simply s of h, yes? But s of h means f of x a minus h. And h goes to 0 from the right-hand side. So this means that I have to calculate this limit. But this is just simply f of a. but you need to explain why. So let me just clean it. I would say that I want to bring this f out and then send limit in. This is not always possible, but it is possible if the limit of this exists and the outer function is continuous at the answer of this limit. The answer of this limit is a, and f is continuous everywhere, including a. So then it means that I can flip this limit inside, and then I can write f, the value of this limit is a. But you have to express that you are using that theorem. So it is not always, let me just remind you about that, that's a little bit subtle. So if I have f of g of x, and I want to send x to a, my question is that, can I move this limit inside and write f of limit of g of x when x goes to a? The answer is yes, provided there are two things happening for you. First of all, this limit at that point should exist, and it becomes a number. The second thing is that your function f should be continuous at the value of that limit. If both of them are satisfied, then you can slip this limit inside over the outer function and put it for the inner function. That's what I did. So this assumption is actually really needed. Otherwise, you cannot use the fundamental theorem of calculus, and you will not be able to pass this limit inside. Okay, so that is this method. Okay, now I want to solve the problem a little bit differently using the intermediate value theorem for integrals. So let me remind you about that theorem first. So assume that you are calculating this integral from a to b of a function. So let me use a letter that a function u of x dx. So assume that you are interested in calculating this interval, but there is one condition here. You know that the function u, whatever it is continuous on the closed interval of your integration limits, yes? It is continuous there. So the intermediate value theorem of integrals guarantees that there exists a constant c within this closed interval such that the value of this integral becomes the value of the function at that point c multiplied by the length of the interval of integration, meaning b minus a. So this is guaranteed by the intermediate value theorem of integrals. So the second method that I want to use to solve this problem is using this theorem, not Hubitel's rule. So what I do that, so let me rewrite everything here. So the question mark is equal to, so if you see, I am supposed to calculate the limit of this expression when h goes to 0. So let me just write it here. So the limit of 1 over h integral from 0 to h f of a minus x dx when h approaches 0 from the right side. Okay, so can I apply the intermediate value theorem for integrals for this integral? Yes. Why is that? Because the only constraint here is that my integrand should be continuous on that interval. Is it? Yes. Because f of a minus x is a composition of f and the polynomial a minus x. F is continuous everywhere according to the problem. A minus x is a polynomial continuous everywhere, so the composition of them is also continuous everywhere, including this interval. So I can apply the integral theorem here that I mentioned to say that, okay, there exists a c where in the closed interval from 0 to h, such that the value of this integral is f of that value, a minus c, and then times the length of the interval, which is h minus 0. So don't get confused. What I wrote here is based off this theorem for just this integral. But I have 1 over h here, and then I have the limit here. Okay? But let me tell you something. I wrote here C belonging to 0 to h. H is not a fixed number because I am sending h to 0 from the right. So I'm making h smaller and smaller. But the point is that for every positive h, I can find C. So this means that this C depends on h. Because if you change x, for example, making h smaller, you're making this interval shorter. So there is no guarantee that for every h, C is the same. C depends on h. To show that, let me write it as C of h. Means C depends on h. C itself is a function of h. Okay? So in that case, if you don't mind, let me take this and write it C of h. Okay. Another thing is that this is just h, this is 1 over h, so they are cancelled. So the bottom line is that I have to calculate the limit of f of a minus c of h when h goes to 0 from the right-hand side. Okay. Again, the question is this. Can I flip this limit in? Here, you have c of h, which is a function of h, is between h and 0. Okay? If I take the limit of this one, when h goes to 0 from the right, the answer becomes 0. If I take the limit of this one, when h goes to 0, this is just a constant, so its limit becomes 0 again. And then we have a squeezing theorem. So the limit of the middle one, when h approaches to 0, because the limit of the left exists and the limit of the right also exists, and moreover they are equal, they will squeeze the limit of the middle one to also be equal to 0. So this means that the limit of this one is 0. And because the function f is continuous and the limit of this exists, yes, this means that I can, again, according to what I mentioned, I can flip this limit in. But this is a constant. I showed that the limit of this one is 0, so this is just a, and this is f of a. So that's also another way to solve that problem. So either you use the Hopital's rule or you use this and a theorem. But you have to, because this is a theory problem, so you have to be very clear in every step that you are using. So you have to refer to the equations that you are using. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.